Yes, very good morning, dear students. Welcome back to online physics class. So, last class we discussed about characteristics of magnetic force and introduction about electromagnetic induction. So, today just I am going to discuss about with what is the Faraday experiment and what are the conclusions of Faraday experiment. Why? Because Michael Faraday only discovered when magnetic a field also produces electric current. Change in magnetic flux or magnetic flux relative to the coil also produces to electric current. Nothing but Einstein experiment means electric current produces magnetic field, but he was experimented reverse. It means a magnetic field produces electric current or not. So he was successfully did different experiments from long 6 years ago, and finally he concluded a change in magnetic flux with the coil is produces due to electric current with the help of galvanometer. So how it is, just I'm going to discuss today with you. See that only Faraday's experiment. Faraday's experiment. See the experimental arrangement, the experimental arrangement used by the experimental arrangement used by Faraday used by Faraday used by Faraday consists of a coil used by Faraday. The experiment consists of a coil of a few tons and a sensitive galvanometer, a sensitive a sensitive galvanometer G is included in series with the coil. Series with the coil. So now just I want to discuss with the Faraday observations. Faraday observations. So this is it is actually experimental arrangement. What is that experimental arrangement? The Faraday the experiment is consists of a coil of few turns. It means turns will be like this, and a sensitive galvanometer is connected within series. Right now, what are the observations from that? See, first one, when the galvanometer is stationary, when the galvanometer is stationary, when the galvanometer is stationary, it means is at rest. Stationary, not galvanometer, sorry. When the magnet is stationary, then there is no deflection in the galvanometer. Then there is no deflection in the galvanometer. Then there is no deflection in the galvanometer. What is that? When the magnet is stationary, then there is no deflection in the galvanometer. See, for example, I am taking that only. Just I am taking a coil. It is a coil. See, a coil. So it consists of a number of turns. Right, it is a C, and this coil is connected to galvanometer in the series. It is a series connection. So it is a pointer for galvanometer. It is actually, what is the meaning of this pointer means, it is denotes the current, right? Whenever it will be deflection means the current will be deflection. So it will be straight means it is, there is no deflection, it will be stationary only. So it is moving like this right side, or it is moving left side means it is a deflection in the galvanometer. Actually deflection, what is the use of galvanometer means, it is used to produce a current. It is used to produce a current. It gives the current, it is used to produce the current, or it generally it gives the values of current. For example, in experiment we are using galvanometer means the galvanometer is just generally it is used to give the values of current. See, it is connected to this coil. So, and this is a magnet, north pole to south pole. Just you have to assume this is a north pole, it is a south pole. It is a velocity, I mean the motion of the magnet is zero. Velocity means the motion of the magnet is zero. So it is a G. It is a G. This one. So a diagram just I'm considering. Understood my point? So when the magnet is stationary, then there is no deflection in the galvanometer. So magnet is stationary here, then there is no deflection in the galvanometer. So second one, when the north pole, when the north pole of the magnet, when the north pole of the magnet is brought towards the coil, is brought towards the coil, then whenever just his experiment is, whenever he brought an north pole of the magnet is towards the coil, then a current flows. He was observed a current flows in the coil, and the galvanometer shows deflection towards the right. So what is his conclusions? Already we discussed magnetic field, magnetic flux or magnet is also produces change in current in the coil. So here it was observed. What is that? When the north pole of the magnet is brought towards the coil, then a current flows in the coil. Current flows means in that experiment, in this diagram galvanometer, then there is a change in deflection in the galvanometer. So if you bring towards the coil, then it shows deflection towards the right. So that I want to discuss with you. It shows the deflection. It is like vertical means there is no deflection. And the second diagram I will draw. See. This coil is connected to the galvanometer. Now there is a deflection towards the right. It is a deflection source. It is a G galvanometer, and here the magnet is coming towards the coil. The north pole of the magnet is coming towards the coil. Is the motion of the magnet. It is a diagram B, right? And the third point, if the motion of the magnet is stopped, you can stop the motion of the magnet. If the motion of the magnet is stopped, then again there is no deflection in the galvanometer, and the galvanometer again then the galvanometer, then the galvanometer again shows no deflection, hence the current in the coil flows as long as magnet is moving, then this is one of the relation he given. If the magnet is does not moving towards the coil, then there is no deflection in the galvanometer. There is no deflection in the galvanometer, then there is no current produced in the coil. So it's the current produced in the coils depends upon moving of the magnet. So again I am drawing a diagram. See coil, coil, and it is connected to the galvanometer. Again here represent a vertical. Vertical means there is no deflection. And here I shows a magnet, north and south, then motion of the magnet is 0. Right? Now fourth point. So if the magnet is moved away from the coil. Before that we discussed towards the coil, now away from the coil, and then the current flows in a direction opposite to that in case 2. Right? See, in case 2 what we discussed here, when north pole of the magnet is brought towards the coil, a current flows in the coil and the galvanometer shows deflection towards the right. But here it is brought towards the coil, but now I discussed we can send that magnet away from the coil. Before that it shows deflection, then current is produced in the coil, but here also shows deflection, but the current is produced left side. Deflection shows the left side. So that only the galvanometer in case B, and the case 2 or case B, here case 2, and the galvanometer shows deflection towards left. I think everyone got it. So how it is means, see, it is a coil. These are the turns of the coil. And it is connected to the galvanometer. It actually now it shows deflection towards the left. So it is connected to the coil again. So it is a coil, it is a galvanometer. Now the magnet is moving away from the coil. The motion of the magnet is moving away from the coil, this side. Right? Yes. Now fifth point or case 5. case 5, instead of north pole and the south pole of the magnet is either brought towards the coil or moved away from the coil, then the direction of induced current in the two cases are opposite to the case 2 and case 4. In the direction of this current is dotted arrow are shown figure. So already this is no need actually. And the next one more point is, in case of the magnet is moved faster with velocity v dash instead of v, then the deflection of the galvanometer is also increases. Note the deflection is more in figure as v dash is greater than v. So I think everyone got it or not, I don't know. See, for example, uh, in the case, in this case, what is a B case? So this is a B case. See, here for example, it is moving with the velocity 20 meter per second. So instead of that, the magnet is moving with the 40 meter per second. So what happens? The galvanometer, the deflection is also increases. The deflection is also increases. So that I want to discuss it with you. So in case the magnet, is moved faster with velocity v dash instead of v, either towards or away from the coil, either towards or away from the coil either towards or away from the coil, the deflection in the galvanometer is increases. Reflection in the galvanometer is increases. Note that and deflection is more in case 5. Case 5 means fifth point comparing to case 2. And case 4 also. Why? Because I told towards or away. Case 2 and case 4. So that see, just nothing is there. Just you can shows deflection is more. See, just you can take. So how we can detect deflection is more means, if there is an experiment is there means, so that by showing that readings we can identify. But here theoretically we can write like this only. So just it is moved towards the coil means, so it takes deflection towards the left, or else away from the coil means it takes deflection in the left. It is right, that is left. See, it is a galvanometer and it is connected to here, but now here I am taking towards the left, towards the right only. It is a north, it is a south. This is, if you take it is moving towards the away from the coil, it shows deflection left, right? And finally last point, sixth point is, so exactly similar observations are made if the magnet is stationary and the coil and the coil is moved either towards or away from the magnet. These are the Faraday's observation from his experiment, dear students.